Hello and welcome to my next Fez Physics presentation on the Toy Crossbow, subtitled William Tell Meets Physics. My name is Bernard Taylor, and if you're interested in online tuition, then please do contact me. But let's move on. I'd like you to stand against that wall with an apple on your head. Please. Why? I want to see if I'm as good a shot as William Tell, and I could play the William Tell overture at the same time. You would have to wear a safety visor. Who was William Tell? Well, I did try this on with an Ofsted inspector, with my class ready to play their part in the drama, and why not? Inspectors should get more involved in lessons, shouldn't they? Anyway, so who was William Tell? He was and is a Swiss folk hero. He was walking along sometime in the 14th century in Switzerland with his young son and refused to bow to a hat belonging to Gessler, the local Austrian chieftain. Austria had ruled or was ruling Switzerland at that time in history. Father and son were arrested and imprisoned. Gessler said that father and son were to be executed, but William Tell could save their lives by shooting an apple off his son's head in a single attempt. In that single attempt, William Tell split the apple in half with a single shot. But before taking the shot, William had taken 2 bolts from his quiver, and now Gessler wanted to know why. William replied that had he killed his son, he would have shot Gessler through his black, wicked heart with the second bolt. And here is my toy crossbow. The dart is there as well. The dart has a rubber sucker on, but most of the energy is stored in this steel strip, which constitutes the limbs of the bow or crossbow. And here I am about to carry out my experiment. The toy crossbow is mounted, clamped vertically, and we can see the string. What we're going to do is to tie on another piece of string and to add masses to that to extend the crossbow string and to measure that extension from the original horizontal position. We can talk about ways in which we could improve this experiment a little bit later on in our presentation. So that's it. So what's this all about? It's to determine the efficiency of the toy crossbow as an energy transfer device. Yes, the energy stored in the crossbow, potential energy, is converted into the kinetic energy of the dart, which is converted into the gravitational potential energy of the dart. But is it as simple as that? We shall see. Incidentally, you could carry out this experiment with those cheap toy bows and arrows that you can get from toy shops. But this is a little bit more superior. Anyway, if we have a force extension graph, we know that the work done is equal to the energy stored, and that the work done, if we have this kind of graph, is the average force, F over 2, times the extension. That is the area under the graph. Now, it just so happens that this type of toy crossbow, it really does give a pretty much a straight line graph, and it obeys Hooke's law. We could also approach this in terms of comparison with a velocity time graph that some of you may be more familiar with. If we have a graph of velocity against time, then the distance is the area under the graph. Oh, and of course, velocity times time in general terms is distance, and we know that the distance is the area under the graph. And it's a little bit similar here. The area under the graph is half times the force times the extension. There's the force, there's the extension, which is, of course, the area of a triangle. In carrying this out, I recorded the load on the string in newtons and the extension of the string from the horizontal position. And we're going to compare the predicted height with the actual height when the crossbow is fired vertically. Fired vertically in a stairwell. My graph here of load against extension shows pretty much a straight line. I've used SI units, I've converted from centimeters to meters. And of course, when we do fire the crossbow, there's the dart with the sucker on it. We need to be careful of safety. Don't lean over the crossbow when firing it. Wear safety glasses when firing it. Those up above the ground floor should, who are measuring the height of the dart with a tape measure, should wear safety glasses. And of course, you should warn other students using the stairwell when you're about to fire. Now, we said that the area under the graph was the energy stored. From my results, stretching the string, the bow string, down to the trigger position, the force was 11 newtons and the extension was 16 centimeters, 0.16 meters, which gives me an energy store of 0.88 joules. The mass of the dart is 2 grams or 0.002 kilograms. So the predicted height of the dart, mgh, and if all that stored energy goes into gravitational potential energy, then mgh will equal 0.88. We do the calculation and we find that that predicted height is a massive 44.9 meters, an unrealistic figure of 44.9 meters, given that the height of the building that I was firing this in was very much less than that. So what's happening? When I took measurements, the height from the ground floor to the second floor was about 7.6 meters. The height reached by the dart when fired vertically upwards was 9.2 meters, measured with a tape measure, which gives us an efficiency of 21%. Now, I could have compared gravitational potential energy gained with the predicted gravitational potential energy gained, or I can simply work out the percentage from this calculation. But it's an efficiency, I think you'll agree, of 21%. So where has some of the energy gone? Well, some of the energy has been transferred into sound energy. You certainly hear a sound when the crossbow is fired. There'll be air resistance as the dart moves through the yielding air, as W.H. Auden put it. It'll use up, or it'll transfer energy to heating the air and heating some of the dart itself. Significantly, there are vibrations in the crossbow. When you're firing, if you put a finger on the metal strip that I showed you earlier, then you really feel the limbs of the bow move, vibrate quite a lot. So we're just about done. But if you were to do this, or if you were to get your students to do this as an experiment, we could improve upon this. First point, don't round the extension measurements. I've rounded them slightly. Clamp that meter ruler in position. Use a set square to make sure the ruler is vertical. Load and then unload the crossbow string to find the average value for the extension in each case. And think about how you would avoid parallax uncertainties when taking these extension measurements. I didn't put in uncertainty bars on the graph. You could do this. Think about how you would do this. And this would enable us to determine a maximum and a minimum value for the area under the graph, and hence a maximum and a minimum value for the stored energy. This would also enable us to obtain an uncertainty in the predicted height. And we love uncertainties in physics. Fire the dart several times and obtain an average value for the actual height reached. And then determine the uncertainty in the actual height reached. So that is Fez physics. That's the toy crossbow. That's the connection with William Tell. So thank you very much and keep working.